Hello, everyone. Okay, welcome to today's lecture. So today we are going to finish our neural networks and backpropagation, and we will move on to convolutional neural networks. Before we start, I have an announcement. So good news, we have a homework 1 available on ETL. So yeah, we posted it a little bit earlier. So please see the ETL for the logistics and the questions for homework 1. And I strongly encourage you to start early, because these are the programming homeworks, and programming homeworks, most of you maybe already know that it takes unexpected amount of time for debugging. So if you start just a few days before the deadline, maybe you may miss the deadline, and that's not a good thing. So especially TAs will be expected to receive a lot of questions right before the deadline. So I strongly encourage you to start early. And if you have any question or anything to clarify, please contact them as soon as possible. And yes, that's basically the thing. Especially the TAs have the office hours. They have Tuesday and Friday, 3:30 to 5 p.m. So each TA will be in charge of each of them. So please contact them if you have any questions. Or you can also post any questions on ETL Q&A board, so that other students actually can take advantage of the answers together. So I encourage that. And yeah, any question about homework? Okay. So let's do a review for the last lecture. Today, let's start with some questions about linear classifier. So in last lecture, we learned that linear classifiers are limited to represent the decision boundary between two classes, especially if they are in nonlinear decision boundary and manifold. So what should we do in that case? So I'm going to ask this to Junho, Lee Junho.
Yes, Professor.
Yes. Yeah. How can we model the data set with non-linear decision boundary?
Can you say that again? Sorry.
So yeah, we learned linear classifier.
Yeah.
And we know that linear decision boundary, linear models are limited to represent only the data set with linear decision boundary.
Yeah.
But we have seen that a lot of data sets have non-linear relationships between the variable and the labels. So how can we model such a data?
Using activation function between the layers, we can approximate some nonlinearity.
Yes, that's right. So not just activation function, but they should be non-linear activation functions.
Yeah, sorry.
Yes, and yeah, that's a good answer. Right. We also talked about a more primitive idea that we can actually map the features, the input images, to some other space, so that we can linearly separate the two classes there. But what Junho said is more advanced approaches we usually use for neural networks. We have the nonlinear activation functions at the end of each layer, so that we can enable our model to represent nonlinear relationships between x and y. Okay, so yeah, that's good. Thanks. And let's ask another question to Eunjung, Kim Eunjung.
Yes, can you hear me?
Yes. So we learned about backpropagation last time. For that, we have represented our model in a graph formation. And each node, we do something for backpropagation. So can you explain what's happening there?
So what you mean is just about the definition of the backpropagation, or?
Maybe you can just briefly explain what backpropagation is and how it works.
I'm not really sure, but it's just a process of giving a penalty of the wrong answers. so that we take a like derivative for each like equation. I'm not sure like how to say exactly, but just taking the derivation for each equation, and that will allow to do like chain rule. That's what I remember, and I'm not really sure.
Okay. Yeah. Okay. I think you remember some pictures and that some terms used
Yeah,
there.
exactly.
Let me ask the same question to someone else as well. Shin Yong-gun, I think you guys are in the same lab.
Yes, Professor.
Yes.
Uh, uh, we we have to optimization to loss for loss. So
So what is loss here?
difference with our prediction and true value.
Yes,
So
that's right.
so we have to optimization that loss. that
Optimize what?
optimize how descent. I'm sorry.
Please try to speak in Korean if you'd like to.
이제 로스를 찾고 그 로스가 이제 그 주변에 어떤 값이 더 어떤 쪽으로 가야 더 로스를 줄일 수 있는지를 백프로포게이션을 통해서 확인한 다음에 이제 최적해를 찾기 위해서 다시 그 반복 작업을 수행합니다.
Yeah. So, so what he said is we have the loss, which is the difference between the ground truth and our estimation, and that actually quantifies how wrong our current answer is, and we updates the weights using that information, and we compute how much each of those weights are responsible for that wrong answer, and we try to compensate it, which is exactly the right answer. So. Okay, so yeah, please review the materials. These are the basics, and I guess many of you are already familiar or at least heard of some of these things in other courses before. But after lecture 8, things will be much more difficult. So please review all the materials and read the reading materials I uploaded on the websites. And if you have any questions or if something is not clear to you, please ask questions. Okay? Great. So today, we will make the things a little bit more complicated, but the basic, the fundamental theory is the same. So do not be scared by a lot of mathematical formulas, but these are exactly the same thing as what we have done before. So backpropagation with vectors and matrices. Until last lecture, we used only the scalar version of the backpropagation, which was much simpler. But in reality, our data is usually not a scalar, but it's a vector or it's a matrix or even tensors. So let's review what is derivative and how do we do that with vectors and matrices first. So the last lecture, the definition of the derivative was this. So when it is scalar to scalar, which means x and y, both of them are scalar values, the derivative means if x slightly changes, how much y changes. So that's the definition of derivative, right? So if x slightly changes, how much will y change? This is what we'd like to estimate using derivatives. But if suppose x is a vector of size n instead of a scalar, we have n values in x, and they are changing slightly. All of them are independently changing. And then how much will y change? That's the question we would like to answer in this case. So partial derivative y with respect to the vector x also works like should be in the form of the vector of size n, because we have n values which is responsible for the change of y, and each of them will be responsible separately. So we need to keep all of those values in our output partial derivatives. So that's shown here. So we have this partial derivative y with respect to x is still a same size vector, and each of those elements is the scalar partial derivative of y with regard to xi, each element. So yeah, these look scary, but actually they are just stacking all the values in the y, in the x, and the derivative works exactly in the same way. Okay, nothing scary here. Okay. And now it's a little bit more difficult, more complex, but still the same. Both x and y are vectors. So we have n values in x and m values in y. So they don't need to be in the same shape. So the number of elements in x and y can be different. But now the question is, if each element xi in x slightly changes, how much will each yj in y change? So this is actually m times this thing, the second thing, vector to scalar. So because for each of xi, how much each of yj changes depending on the changes in the vector x, that is exactly the same question to this, vector to scalar. And now we have m of them, right? So the output should be in the form of matrix, which is size n by m. So partial derivative of y with respect to x is given as this, and each element ij is containing the scalar partial derivative of yj with regards to xi. Okay, so here what you need to remember is when it is scalar to scalar, the derivative is also scalar. If it's vector to scalar, then it's same size vector. And vector to vector, then the shape is the matrix with size n times m. Okay? So let's do that again with vectors. We have x, y, and z, and the forward pass is the same. Whatever the function defines, we just do that. So we have the output z. And let's suppose we have the dimension of each of these vectors. Vector x has dimension dx, which is some integer, like 10, for example. And dy is another input vector, which can be also in different size vector. Let's say it's 20. And dz is the output of this function. So the dimensionality of this can be anything arbitrary. So let's say this is 3. So 10, 20, 3. So they can be arbitrary integers depending on what we take as input and what we compute inside the function, right? It's the same. Now let's compute the partial derivatives. So remember, what we do with backpropagation, in each node, we receive some upstream gradient. Whatever it is, we receive some upstream gradients from the later nodes. So these are just given, right? And at the very last node, we know that that's always 1, scalar 1. But in the intermediate nodes, we receive something from the followed nodes in the computational graph. So that we call that as upstream gradient. And let's see that what shape of this should be. Right? What's the meaning of this? We have the loss, which happens at the very end of the model. And we need to compute how much each element of these vector z contributed to that. So that's the definition of this gradients, right? So the shape of this gradient should be the same as this output vector. So here's what you need to remember. Forward pass and backward pass, the dimensionality of each variable should be always the same, which means they are in the same edge like this. Both forward pass and backward pass, their shape should be dz dimensional vector, because each of these elements are responsible for some errors, and we need to quantify them separately. Okay. And then what we have done after this, we receive the upstream gradients, and then what we do. Anyone remember? Anyone in the chat? I heard some chatting message, but I don't see. Oh, I'm gone. Okay.
So next, we will calculate local gradient and downstream gradient as well.
Yes, that's right. So we compute local gradients with this function, right? So we compute local gradients here, and local gradients should be computed for each input to output. So we have partial z, partial x, and partial g, partial y. And the shape of this, because these are the vector and this is vector 2, so we apply the principle we had in these slides, vector to vector. So the gradient should be in the shape of matrix, and where the size is the n times m, where n and m are the shape of each input and output vector. So remember that. We apply that here. So the local gradient, the shape looks like this: dx times dz, because this part maps the dx dimensional vector to dz dimensional vector. And here is the same, dy dimensional vector to dz dimensional vector. Okay? Nothing hard. It's just, theoretically speaking, it's the same, but they just look scary because we have too many variables here. Okay. And then what we do is we compute the downstream gradients, which is multiplies the local gradients and upstream gradients. Remember that? We have seen some examples last time. So here we compute, we actually multiply this one and this one. So let's check the dimensionality. It's dx times dz, and this is dz times 1. So the output should be dx times 1. And shape of this, so what we computed from the gradients is dx times 1. And that is, we see that that's the same as the input dimension, which is correct, right? And same thing happens here. So output size is dx dimensioner and dy dimensioner. And they are just outcome of the matrix vector multiplication. Okay? Okay, done. So remember this, gradients of variables with regard to loss have same dimensionality as the original variable always in all the edges. So if that's not satisfied, something is wrong. And you're going to do this in your homework. So please review this material if you're not familiar with this. And you may use this gradient, the dimensionality check for sanity check when you code that. So let's see some examples here. So this function computes max of x, which is input, and 0. So it outputs the input as is if it's positive, and output 0 if it's negative. There's some function. And suppose we have the input, which is this vector, 1, -2, 3, and -1. So when we do the forward pass, we just compute it. So each element which is negative becomes 0, and all the positive values are survived. So 1, 0, 3, 0 is the output. Okay. Then suppose we have the upstream gradient. This is given from the next node, so we don't know why, but these are just given. And we check that these are in the same shape, which is correct. Okay. Then what we need to compute is the local gradients in this node. So let's compute that. So local gradients of a vector is vector of gradients for each element, which is scalar. So each of these fxi is max of each element as exactly as what we computed here, x to z. We do that element-wise, right? So this is the function. And then we compute the partial derivative of this function with regard to all other xj, or other elements in x. So then we have 1 if I and j are the same, and if xi, which is input, is larger than 0. In that case, we have output x. So the partial derivative with regard to x is 1. And if it's not, which is I and j are different, or if this is negative, then we have 0. So as an outcome, so we will have the shape of this because z is 4-dimensional, x is also 4-dimensional. So the local gradient should be the shape of 4 by 4. And as we know, because I and j are different, then it's always 0. So off diagonals are 0 here. But on these diagonal elements, they are 1 only if the input x was positive, which the survived elements. So in this particular example, we have 1 in the first and third row or column, and zeros in the others. So are you following what's happening here? Okay. So we computed. We are actually doing exactly the same thing as last time, but we have just multiple numbers instead of one, single one. So from the upstream gradients, we computed the local gradients and multiplied them. We can compute this matrix vector multiplication, which we have this. This is the downstream gradients we computed. So please practice this. You may try some other examples of this function and other examples. And we are going to have some similar questions in the exam later. Okay. Okay, the very last slides, which will be even more complex. But if you know what we are doing exactly, it's still exactly the same thing. Now, x, y, and z are matrices, not vectors. So input x is dx times mx. These are all some integers specifying the size. dx times the mx, and this is dy times my. This is dz times mz. All of these are matrices. And all of these can be different depending on what we are doing in this function f. So what should be the shape of the upstream gradients? Yu Jaeyeon?
Yes.
Yes. What should be the output size of this? Size of this gradients.
The shape of z is dz by mz.
Yes. Why?
Because the value of loss is scalar, so it is the same shape of the vector z.
Yes, that's correct. Yeah, thanks. So yeah, we always have the same shape in the same edges. So z and this gradients are in the same shape. And then what we do, we compute the local gradients, which is exactly the same. Partial z, partial x, partial z, partial y. From the function, we just compute this mathematically. And then the shape of this is this complex, but it's still the same, which is this size times this size, input size times output size, which is this. And it's the same here, right? Then what's the shape of the downstream gradients? We multiply these two, right? So this one and this one is multiplied. So size is this size times this size. And we see that these are the same, which is valid matrix vector or matrix multiplication here. So what survives is dx times mx times 1. So the size is dx times mx. And the same is here. So if you just see the slides, these look very scary. But you may now know that it's exactly the same as what we've done in vector to vector or even scalar to scalar. So we can apply this to any size of any dimensions of vectors or matrices and any types of data, any kinds of data which can be represented as a tensor. Okay. Any question so far?
Oh, so I might miss